Okay, so in this video, this is kind of our second part really, because we looked at sort of some simple pulleys from before, and now we're going to have a look at a popular situation, which is a horizontal and a vertical pulley mixed together. So just a reminder really to start with, what we would do is we would work through weight, reaction, resistance, friction, tension, thrust, and we're going to do this for each of the pulleys. Then we're going to kind of... So we're going to think about those, use them to make our force diagrams, okay? What will we do after our force diagrams? Well, typically we're going to use F equals ma for both, okay? And then whenever they're connected, we tend to sort of get a situation where we can sort of add the equations. So sort of some things you're going to see as we go through on the next bit here. When we do this, you're going to see a reaction, okay, a weight, a tension. There might be extra sort of forces here, depending on the question. We might have friction, for example, but you're going to see at the very least those forces. Whereas for this one here, maybe we can do M1, M2G. We're going to see weight again, and tension, and often that's going to be it. Okay, so look out for these on the next part. This is like sort of the most basic connected situation that you can get. So here we go. Let's give it a read first. A block of mass 1.2 kilograms rests is sometimes a SUVAT indicator, isn't it? On a rough horizontal table. Okay. Right, let's just deal with that first sentence. So I'm going to do 1.2 G, and I'm going to cross that off. Rough. Well, rough, I might be being told exactly what the friction is. Otherwise, so I'm just scanning the question now for a mu value. The frictional force. Okay, so interesting. Look, this is one of those where I've been told the friction rather than mu r. Sometimes you have a mu r sort of thing, whereas here I've been given a force of 4.2 that they want me to use. Okay, so there we go. I think I'm finished with the table, and I think I'm finished with that piece of information. Let's read the next sentence. So, it's attached to a light, inextensible string. Okay, these are sort of good words for ends of questions normally. And the string tells me that I want to be doing this. It also told me that it's inextensible. So while I'm here, I could also jump ahead and do that and write the same letter for both of them. So it's a light, inextensible string. I'm going to go like that. I think I've handled that pretty much. I'll just go like that because those words might be useful. Which passes over a small smooth pulley. Okay, that's pretty standard at the edge of the table. Yeah, so, you know, sometimes you might see people do this as well for their diagram. I'm not going to do that. I think that's fine. The other end of the string is attached to a 0.8 kilogram mass B, which hangs freely below the pulley. Okay, let's put the 0.8 kilograms, so that needs to be 0.8 G. And I think we are pretty much there. Scan the first part for anything. There's some assumptions in there. It hangs freely, just lets you know that it's not sat on a table or anything. Okay, let's read some more. The system is released from rest. So there we go. There's a strong feeling that this is going to be sort of a SUVAT question, perhaps later. This is often a sign to use a U equals 0 somewhere. After release, B descends. Okay, so there's some more specific information linking an S and a T together there. Okay, so before we go too much further, I think it's probably just worth us going back here and thinking, have we accounted for all of our forces? So weight, reaction, resistance, friction, tension, thrust. Well, weights I have done for both of them. Reaction, right, this would actually have a reaction. It might not be useful in this particular question, but because it's in contact with a table, there is a reaction. There's no reaction because this hangs freely. Resistance, yes, there was a specific resistance of 4.2 given to me, which was also the friction in this case. Tension is there, and there were no other forces. So my force diagrams are complete, and that's a pretty common kind of force diagram question. Okay, we can go and we can read the next question, but to be perfectly honest, as we said on the previous slide, for A and for B, we know that we're going to have to write equations of motion. So that's F equals ma for both. Okay, so for A, what's the resultant force? Well, I'm going to take this direction as positive and positive this way, because that's logically where it would all start moving. So T is a leading force, 4.2 is acting against. These forces are perpendicular, so they're not involved in this F equals ma that I'm writing. They equal the mass, which I can see is 1.2. 1.2 times the acceleration, which I don't think I know. No, I don't know that. It's not g, okay? It will be a value less than that. So that's for A, and for B. So look what we're doing. We're kind of considering these separately, aren't we? This one doesn't really know that this one exists, okay? It just has tension. That's how the things are really being connected together. So for the next one, 0.8 g is sort of the driving force that goes with the direction, and then it's minus t, isn't it? What's it equal to? It's equal to 0.8 a. So this is sort of the second main step. So the first one really is the force diagrams. The second one is this, and then the third we said is often adding these together. So the reason for that is t and minus t, you'll get this situation very often where they'll cancel each other out. So let's add them together. I'm going to get 0.8 g plus a minus 4.2 equals 2a. And in fact, it's almost sort of solving itself really, isn't it? 0.4 g then minus 2.1 will be equal to my a value. And this first question here will often be find a or find t, and you can kind of see now why it's doing that, yeah? Because that's sort of the most useful result that you end up deriving straight away. So I've got my a value there, so I would just do 0.4 times 9.8, I think it said in this question specifically. Sometimes it's different, so watch out for that. Minus 2.1 is going to be equal to my value, okay? And how about where the question goes next? So for the next one, they'll talk about find the tension in the string. So if you look at the information there on the screen, that should give you some idea of kind of where we're going to be going with it. So let's just work that out now. 0.4 times 9.8 is 3.92. So 3.92 minus 2.1 is 1.82. And once you've got your a value, you can feed this into one of these equations, maybe this equation here, and you can find your t value. So t should be equal to 4.2 plus 1.2 lots of 1.82, which would be equal to what? Well, let's do 1.82 times 1.2, and then we'll add 4.2 onwards, and we get 6.384. Okay, or we could say then underneath 6.4 newtons. Okay, so that's for my I'll do there. That's my part A, and then that's my part B. That's for my A and for my B. And although there was lots of SUVAT question, that wasn't actually the focus of this one, it seems. Finally, explain how you've used the fact that the string is inextensible. So we had a feeling that this one might come up. Okay, so the tension and acceleration are the same. Okay, but that's our basic situation.